Hello, welcome. Here we are in chapter 15 and talking about energy. So let us get to the slideshow. Here is energy, and here are the learning objectives for this chapter. So first of all, let's talk about energy. What energy is. Next slide. Let's talk about where we get our energy coming into the earth. Not surprisingly, we get it from the sun. And we get it from various other sources as well. And energy out, this should balance out. Does it balance out? No, I guess it doesn't. But it's about the same. And there's the energy in, there's the energy out. Energy is defined by the capacity to do work. The physics definition is better. It's force along the path length as in definition of energy. Also transfer heat, well, depending on what you mean by that, I mean, that could be considered work as well. But that's the definition of energy. And we typically use joules for energy, and the unit of power is watt. The difference between energy and power, energy divided by time is power. So, for instance, my first car was a Nissan Sentra. It could definitely get to 60 miles an hour. So it was 0 to 60 miles an hour in like 20 seconds. It had one heck of a pickup, let me tell you. But you can do the same thing with a Ferrari in like 2 or 3 seconds. And another fun fact, a cheetah. I was looking at a cheetah. Actually, might be able to do. I mean, definitely could outrun my car, my original car. I don't know if a cheetah could run faster or get up to speed faster than the Porsche, but cheetahs are fast. They can get to 60 miles an hour in like 2 seconds. So amazing creatures. Anyways, sorry, back to chemistry. I like fuzzy animals too. But power is energy divided by time. So when you have high power, that just means a lot of energy is used in a very short period of time. Okay, so two types of energy. Potential energy is stored energy, and kinetic energy, energy of motion. Heat and temperature is kinetic energy. Potential energy is either gravitational potential energy, could argue nuclear potential energy, so all matter has potential energy that way, and also chemical potential energy. So the biosphere, and we've been talking about so far, if you're following the chapter, hopefully you're following the chapters in order, we talked about the atmosphere and the Earth itself and the hydrosphere. Well, the biosphere is only a really small part of that. And much of the radiation coming from the sun is put back out to space, and much of it drives the water cycle, evaporate. It takes a lot of energy to evaporate water. Only a very small portion is absorbed by the biosphere. So even we ourselves are slightly photosynthetic. We can use ultraviolet B radiation with cholesterol to form provitamin D3. So we can get some nutrients from sunlight, but we're not nearly as dependent as plants. So I mean, we don't really need sunlight. We can get it with our diet, but we like sunlight. It makes us feel good. And part of the reason why is because we are in fact slightly photosynthetic, but not like plants. Plants are very, very reliant on, at least the ones that photosynthesize. I guess you could argue that well, it depends if you think fungi or plants. I guess they're a different kingdom. Okay, well, moving on. This is the photosynthesis reaction. It's 6 carbon dioxides plus 6 waters, and the chloroplast with a photon produces glucose and oxygen. So it's kind of interesting the way the process works. Chloroplast has got a magnesium center and has carbon around it, and the sunlight excites that, and then it activates the rings, and then the chemistry happens where it goes and rips apart carbon dioxide and water and forms glucose. It's pretty cool, actually. Okay, so chemical reactions. We didn't really cover this before, but let's talk about it now. What increases a chemical reaction? Temperature, concentration, and the presence of catalyst. Okay, so atoms and molecules around them, they have electron clouds, and in order for things to react, the atoms and the molecules, well, the atoms need to rearrange. And since electron clouds are negatively charged, there has to be enough energy to overcome the repulsion of the negative electron clouds. So if there isn't enough energy, that's where temperature comes into play. So there isn't enough energy. There's not enough energy to overcome that barrier. So that and specifically there's a temperature called the activation energy. There has to be enough energy to overcome the repulsive barrier. Temperature and concentration have a similar effect, number of collisions. So in order for things to react, they have to have collisions. They have to collide together. So the more collisions, the more likely a chemical reaction is to take place. If you study chemical reactions, 1 out of every 10,000 collisions causing a chemical reaction is actually considered a very fast chemical reaction. So the collisions, it's amazing to think that chemical reactions even happen when you see them. Like when you study them, like, wow, do these things ever actually react? But collisions, the more collisions you have, the faster the rate, the more chemical reactions. And how do you have more collisions? Well, you have more stuff. Higher concentrations means more stuff are going to react. Temperature also helps because they're moving faster, which means things are moving faster, more collisions. So temperature and concentration help by both of that. Also the presence of a catalyst. So catalysts work by causing an alternate path and lowers the activation energy. So that means that the chemical reaction can happen at a lower temperature, or it can happen, it just gives another way that's more convenient for it to react. So it could be on the surface of platinum, for instance, or you could argue with an enzyme. Enzymes kind of wrap around the molecules, and then the collision that happens, it happens a perfect collision every time. And catalysts are very important, especially enzymes in biological processes, because the shape of the molecule is very, very important for biological processes. Okay, so energy chemical reactions there. All right, back to well, I guess we're still in chemistry. Exothermic reactions release heat, and endothermic reactions absorb heat. So different processes. We talked a little bit about that in nuclear chemistry. So here are some exothermic processes. Water freezing actually releases energy, then melting ice absorbs energy. So that's why if you put ice on something, it feels cold. And actually freezing of water releases energy. Sometimes fog forms on the surface of freezing water, and that's because the freezing of the water vaporizes some of the water. Condensation of water vapor is exothermic. You put your hand in steam, it hurts. Evaporation is also cooling. So although when you're wet and it's a hot day, it does cool down. You could argue it's a heat transfer coefficient, but evaporative loss. So maybe if you take alcohol and put it on your skin, like rubbing alcohol, and it evaporates, it feels really cool. That's from that. The wetness, if you're wet, much of the heat transfer is actually from the heat transfer coefficient, which is more of a engineering. I have an engineering degree, so I understand a little better than the scientists that wrote this book. But that's also an engineering problem. Metabolism is exothermic. Photosynthesis is endothermic. It absorbs energy. Forming chemical bonds tends to be exothermic. Breaking chemical bonds is endothermic. So batteries, discharging is exothermic, releases heat, and charging the battery requires energy is endothermic. Okay, here's the first law of thermodynamics. It's the conservation of energy. So that's the first law of thermo. Second law, here's the first law. Second law is the entropy of the universe is always increasing, which also relates to heat flow. Heat flows only from hot to cold. So that's because of entropy. And entropy, it's probability. So entropy is really all about probability, and this was a big deal in the 1970s, even before. Actually, even in the 19th century. 1970s, people were worried about the heat death of the universe. Before that, in the 19th century, many people still believe in fate. And they thought, there is some guiding force pushing the universe forward. And once we figure out what the guiding force is, we'll just know everything, and everything will be cool. And then they find out, like, oh, many processes are actually because of probability. And probability is what drives many things in the universe. And that was quite a shock to a lot of people, saying, oh, so it's mathematics, not necessarily, and probability, not necessarily some sort of guiding force driving us forward. So, so entropy is just plain old probability. And not included here is a third law of thermodynamics. Third law is trivial. It's the third law of thermo is that the entropy of a perfect crystal at 0 Kelvin is 0. That just is the definition to helps define entropy. Entropy is absolute, meaning that that there is that it's not a relative scale. There is a absolute scale. Temperature is also absolute. At least Kelvin temperature is absolute. There are relative scales. Celsius and Fahrenheit temperatures are relative scales, and also enthalpy is a relative scale as well. So, for instance, you relate it to something, but temperature and entropy are absolute. There is 0 temperature and 0 entropy, and not just because we define it but that way, but that's by the nature of having one state for entropy, one possibility for entropy, and having no motion for temperature means that we can relate it, that it's not related, necessarily related, but it's absolute. Okay, so people power, early uses. We originally got energy by hunter-gatherers. And our first fuels were plant materials, so fire, even non-human ancestors did it. Australopithecines could use fire. Homo erectus could use fire, and are the kind of sort of humans, the Neanderthals, that have bred into the the modern contemporary human Homo sapiens. They used fire. So, but even today, we about 1/3 of the world uses wood and dried animal dung. So also water wheels and windmills, those converted the kinetic energy of water and air into mechanical energy. So we still do this, of course, for electricity generation. But nowadays, we primarily use fossil fuels to produce our energy. And fuel is basically, it's a reduced form of matter. And when we burn it in oxygen, you can burn it in other oxidizers, but oxygen is the most convenient one here on Earth because it makes up 1/5 of the atmosphere. And so here are fuels, the reduced substances, and then the byproducts, the oxidized products there on the right. So you can also burn things with other oxidizers like chlorine or fluorine, but here on Earth we use oxygen. So this slide, when I was reviewing the slides, this slide is not entirely accurate, but just so you know that as petroleum natural gas will be consumed and no longer be used as fuel. That's not entirely true. For the United States, our proven reserves are 33.4 billion, but this is not including many other reserves. This is not including offshore oil. California has about 150 billion barrels of proven reserves offshore, and that's also not including oil that's in nature preserves as well. So also these reserves are refilling, which is kind of strange that many of the reserves are actually coming back up. Which there's something that this book is using the old definition of fossil fuels. I think soon the idea of fossil fuels is going to go away, meaning that that the source of things like petroleum and natural gas is not going to be from dead plant matter and dead dinosaurs. The competing theory, or not theory, it's a hypothesis called the abiotic hypothesis. So the idea is that petroleum, light and heavy crude, natural gas and some coal is from the Earth itself. And among this, although this slide looks dire, there's much more reserves in natural gas. So there's something called methane hydrates. You find them in Alaska, Siberia, and the bottom of the ocean, especially in the bottom of the ocean. We talked about ice, and I said the most common type of ice, like frozen water, floats. There's other types of ice that sinks, and in the bottom of the ocean, some places hundreds of meters thick, you have methane hydrates trapped in ice, and that's the amount of hydrocarbons in there is ridiculous. And not mentioned here, the United States, we also, if you look at oil shale, we have over 1 trillion barrels of oil equivalent in oil shales in the United States. So we just kind of have to change the form of what we look for. And I mean, I know that petroleum is hard to get in the bottom of the ocean, but it looks like that petroleum is being replaced faster than we thought. And the idea is that that water and carbon dioxide and heat and chromium and iron rocks in the mantle and the crust is forming petroleum, and then that's going towards the surface. So that's the abiotic hypothesis. And other sources for this is that we're seeing hydrocarbon lakes and Titan. So besides the Earth, Titan, it's a satellite of Saturn. And we see hydrocarbon lakes. And we also see a great deal of methane in Titan. There's also nitrogen atmosphere in Titan. And we also see methane in places like Uranus, the other planets. So where are all these organic molecules coming from? And the answer, I mean, the obvious answer is well, we don't think it's from living creatures, especially with the amount of hydrocarbons that we're seeing in these other places. So obviously, methane is produced in other ways than by plants and living creatures. And so this is going to change in the future. I think we're going to get away. We might use the word fossil fuel still, but the belief won't be that it actually is a fossil fuel. Russia teaches it. So if this was a Russian chemistry class, they would teach that that there is no such thing as fossil fuel. And they would probably, the next sentence is, the stupid Americans believe it's from dead dinosaurs. So Russia has already adopted this in their curriculum and such. So we got some time. Old habits die hard for us. So we'll see. But pretty soon, I think my own personal feeling is that the fossil fuel concept is going to go away. And like I said, this slide is a little dire. There's much greater reserves. This is, I guess, they're not. I guess this is showing proven reserves and reserves that haven't been discovered yet, and also not including the ocean reserves as well. Because if California has 150 billion barrels, imagine where else there can find reserves. And we're not even talking about Antarctica too. So we'll see. Future has to say. But eventually, but the point of this, eventually, even if the Earth is producing it, we eventually are going to run out of the hydrocarbons. So it delays it by a couple hundred years, but still, it's not going to happen within our lifetimes. That's for sure. Okay, so coal, just good old carbon. Coal is good old carbon, and also here are different grades of coal. So the best grade of coal is anthracite. We've mined quite a bit of it. You find a lot of it in Pennsylvania. That's a good place to find it. And then we're going down to the different types of coal. Although the more expensive coals now actually tend to be the low in sulfur. And but there they are, and we have lots of coal. So America has plenty of coal. Australia has a huge amount of coal. So if you look for a place that has a huge amount of coal, it's Australia. And it's very abundant. It's not the most abundant fossil fuel. It's methane hydrates are, methane hydrates. The reserves there are ridiculous. There's lots of heavy crude too. Venezuela has lots of heavy crude, as does Canada. So they included only light petroleum and that heavy crude. There's much more of that as well, and then also the oil shale that we have in the United States. It's the ridiculous amount of hydrocarbons we have. It is inconvenient. The most convenient is light crude. Light crude is by far the most convenient. It's a liquid. You just pump it from the ground, okay, and then you put it in a pipeline and you push it somewhere. It's relatively unreactive, so you can push it in the pipeline and you send it off to be to be processed. Natural gas is then the next easiest to use because, well, petroleum is nice and dense in fuel and fuel power. Natural gas is not as dense in energy density, but it's still pretty easy to use. It needs to be refined, not as much as petroleum. Petroleum needs to be refined more, but natural gas doesn't need to be refined all that much. And coal is a pain. It's a solid, so you have to mine it, so you have to dig it from the ground. And also, as you're digging it, you can't just dig it all out because you have to put supports up. Otherwise, the ground will fall on you. So that's a problem. And then you can't put it in a pipeline. You have to put it in a car. You have to put it in a cart, and you have to truck it around by rail or by truck, usually by rail. And then it's just hard to use because it's solid. So it's inconvenient. And also, it tends to be high in sulfur, which makes it more pollution. And but there is some nice things about coals that we can use to get coke. Coke is used to make iron and steel, and it's easier to use coke from coal than it is because you can make coke from wood, but it's just a little more difficult. So also you can take volatile materials to make coal tar, which I've used coal tar shampoo before to help treat dandruff, for instance. So you can use it for other things. And here's the carbon cycle. This is something we don't entirely understand, but we're working on it. Much like the abiotic hypothesis. So our understanding may change. The idea of the cycling is similar. It seems like the core of the Earth has much more. Has much more to play as also heat and pressure with water and carbon dioxide to produce those other hydrocarbons, light and heavy crude. But we have basically the carbon cycles between the atmosphere and the ground, and not included is, like I said, the core of the Earth, which will probably be included in future science classes. Not right now, though. So not that's where we're going, but we're not there yet. At least not in the United States. If this was Russia, this would be a different slide. Okay, so natural gas. So natural gas is a little different than petroleum. Petroleum is fairly consistent, especially light petroleum is fairly consistent in its composition. Natural gas depends on where you are. There's differing components. So like the natural gas that we have in the United States, we have in some areas there's a bit of helium in it. So we get a lot of our helium from our natural gas. And right now, though, helium may become a more valuable resource in the future. We have a stockpile. As I'm making these slides, like Congress, we had a strategic reserve of helium, and Congress has decided to close it off. So we're getting rid of the strategic reserve of helium, and that's where we get most of our helium from. The strategic reserve of helium was from World War One. When we were using zeppelins and for bombing, getting rid of U-boats. So, but we hoarded a bunch of it. We can still generate it from natural gas, but other areas, so the non-United States natural gas doesn't have as much helium. So the natural gas from Norway, for instance, is very different than natural gas in the United States. But the primary component of all natural gas, though, is that it has quite a bit of methane. in it. That's the primary component. And the smell of natural gas, actually, we add that ourselves. It's methylthiol, CH3SH. So that's when you smell the gas. We put that in there because natural gas tends not to smell, well, especially not methane. We add that to make it smelly. And we humans, we can smell sulfur down in the parts per trillion range, and we also don't like it. So I mean, let's say we made natural gas smell like strawberries. You know, like I like the smell of strawberries. Like, wow, this stuff smells great. I'm just gonna sit here and I'm gonna sniff it for a while, right? We put a really smelly substance like, ew, that smells bad. Oh, it's dangerous. Oh yeah, let's get the heck out of here, and let's tell somebody there's a leak. You know, so that's one of the reasons why we picked that. But we can use it. We mostly use it for fuel. And petroleum, liquid hydrocarbon. So we use this. This is what our primary fuel is. It also drives our chemical industry. It's a very complex mixture. And assuming octane, that's what we have there. So that's for octane in cars. But so petroleum is a big mixture, and we separate it out. The light ones we get for natural gas, so fuel. We have a little bit of natural gas in Hawaii, but it mostly is just the tops from the distillation column. We don't have natural gas per se. It's actually from our distillation of petroleum. And then gasoline is the next part, then kerosene, and also diesel fuel. And kerosene is used for jet fuel as well. Heating oil is the next part, and then lubrication oil. And then the leftovers is asphalt, used to make our roads, and a little bit for paraffin wax, although paraffin wax is becoming more expensive. Technology has gotten much better for distillation. We can do a couple things. We can do what's called cracking molecules. We can take long molecules and crack them into smaller molecules, and then we can reform those molecules to make other things. For Oahu, we the distillation columns there. One of the major things we export in Hawaii is jet fuel. So our distillation columns are actually made to make a lot of jet fuel because we have a lot of planes land, a lot of planes take off, and we have the military here. It's the center of the Pacific Fleet, so the Navy has a very big interest in Hawaii. Also, and of course the Air Force. The Air Force uses quite a bit of fuel. We have bases here, so the military and also civilian use, there's quite a bit of jet fuel. Most distillation columns are tuned toward making gasoline in large amounts. We still make gasoline, of course, on Oahu, but we have our columns tuned to make more kerosene, more jet fuel. And this is a distillation column, so we have different stages, and it's a fractional distillation column. And this is part of the story. This is how it used to be. We can also, like I said, we can crack molecules and we can reform them. So this is the cracking. You have a long hydrocarbon, and you crack it into smaller ones. And then those smaller ones you can reform into, or if you take a long one, so you don't, the really long hydrocarbons that were used for paraffin and for asphalt, we have been now cracking them to get more fuel. Actually, so a barrel of oil, when we say a barrel of oil, it's 45 gallons. We get about 55 gallons of product from a barrel of oil. So we're not creating new matter, though. It's the same mass. It's just when we crack the liquids, they become less dense. So we can get more material, more products from it. It's, like I said, it's not matter. Matter is not increasing, just the volume. And it's from cracking the molecules and reforming them. Okay, so and modern day, or I should say contemporary gasoline does not run as well on our high compression automobile engines. So going back in time and in your DeLorean, well, I guess if you had the DeLorean that was made back then, I guess that would, you know what, it would still hold. still hold with Back to the Future, but uh, it wouldn't. The previous ones wouldn't work as well. So octane, the higher the octane rating, it's an anti-knocking process. Knocking is when the fuel combusts before the spark plug, and it makes the engine shake a little bit. So the better ones are the branched octanes. So we don't really use heptane anymore. We tend to use the aromatics, the cyclic compounds, and then the branched compounds in our gasoline now. We don't have the normal. Normal means straight change. We don't have the normal molecules in gasoline. We use the normal uh, hydrocarbons in kerosene and especially diesel. Diesel really likes the normal ones. Kerosene, we put the aromatics also into kerosene, at least here in the United States, and the civilian aircraft use more of them because the aromatic compounds make more soot, and we really don't care about soot coming from the jets. Soot coming from military craft though can be tracked on radar, so they use different blends for the military. Okay, so gasoline. Already mentioned that. Alternative fuels. So we can make about anything. NASCAR, the cars there run on ethanol, but we can really do whatever we want. The thing is, gasoline, it's so easy and convenient. I mean, gasoline is jam-packed full of energy. It's really easy to use. It's relatively unreactive. Um, Ethanol, even E85 mixtures, 85% ethanol. Why do we have 15% gasoline? It's to start the car. It's to turn it over. It's much easier to start a car with a gasoline than it is with ethanol. So that's the reason why there. And E85 has about 2/3 the calories, the energy of regular gasoline. So you can't drive as far on E85 than you can and on 100% gasoline. Diesel fuel you get from uh, the straight normal hydrocarbons. Biodiesel works pretty well. There's some issues with biodiesel. It doesn't have the same shelf life that diesel fuel does. It spoils more easily. The other thing is it gels at low temperature. In Hawaii, it wouldn't be a big deal, but in Alaska, you couldn't. It would be really hard to run um, uh, a truck in Alaska, at least during the winter time, on biodiesel. The fuel would just freeze up, and it's out of the question for a jet plane because if you're up in the air, it gets cold, and then I would not want to be in a jet that runs on biodiesel. That thing, you'd have to heat the wings to keep the biodiesel going. And then if you landed somewhere cold and they turn off the engine, then you have to wait till the springtime to take off again. So biodiesel would be a bad idea for a jet. But I mean, for a blend, and most biodiesel is a blend anyways. Biodiesel, same thing with ethanol. It dissolves the tubing, the fuel tubings. So don't put biodiesel in a regular diesel truck. I mean, it's fine for the engine. It's just the tubes. You have to replace all the tubes. Same thing with E85. Any car can run off of E85, but you have to replace the tubing. So that's one of the problems. You have to use special tubes that are less reactive, that won't react to it. So that's one unfortunate thing about gasoline and diesel. It's just such an easy, great fuel. It works so well. But we're working on it, seeing what we can do. Another one, I guess they don't talk about it, but butane is another one that's looking at close to the energy density of gasoline. Okay, so what else can you do? We can gasify coal. I worked on a company that was looking into doing this. Gasify coal, and that way you can keep the gasified synthesis gas that comes off would be used to make electricity, or you can make other products. Electricity is got to be the most convenient fuel of all, right? I mean, using electricity. Uh, like I said, it's convenient. It comes in through wires. It doesn't smell. All these types of things. Okay, so how do we generate electricity? Most of it, about 90%. Well, if you don't count the 20% from nuclear, so about 70%. Oh, I shouldn't say that because we can use turbines for what do we call it, for the natural gas. Okay, let me think. This is going to be, I guess, coal. We get about half to a third of our electricity this way. Conflicting sources on this. But either way, you have the idea. You have a boiler. You burn the coal, and then you boil water, and then the steam goes and turns a steam turbine. And then you have a gear shaft, and you have a generator. What a generator is just a bunch of magnets that spin around a wire, and those magnets induce a current flow in a wire. Okay, and then the steam that comes off is then condensed and then cycled on through. So then this river water, lake water, whatever, that promotes thermal pollution to the environment that way. But this is generally how we get our electricity, is by this way. This has been going on. Coal is becoming more and more out of style. Natural gas, many natural gas generators are just turbines, which means they have a rotary engine. It turns it and it's like a rocket, and it spins the magnets around the generator that way. It's not as efficient as burning, so the turbines tend to be a little less thermally efficient. This way of doing things is actually fairly thermally efficient. And nuclear power. This is how nuclear power works. We talked a little bit about it with nuclear chemistry. You have typically uranium fuel. You have a stack, and some of these words are from the original nuclear reactor. The first nuclear reactor happened in Fermilab underneath the stadium in Chicago, and the pictures are incredible. And some of the terminology, the pile. It's a pile of uranium oxide, and then you have the axe. So they had control rods. So if you look at the picture, people are sitting there. The workers have their shirts off because it's really hot in there because you have a nuclear reactor, and they're putting the control rods are basically boron taped on to wooden 2x4s that they're sticking on there with athletic tape, and then they have the axe. It's a guy sitting there with an axe with a rope tied to it with a bunch of control rods that would fall down and turn off the nuclear reactor. And this is all done underground. So same terminology. The pile is the nuclear reactor, the pile of uranium pellets. They usually clad them in something like niobium that's really hard to melt. Of course, the fuel could also be plutonium. Plutonium is made naturally as well by transmutation, but it originally starts out as uranium. And then the control rods, depending on the control rods there, they can raise them up, lower them to absorb the neutrons, and that speeds or slows the nuclear reaction. And then here, this type of reaction they have, this is known as a pressurized water reactor. So you have water that touches the core. The nice thing about water is it also absorbs neutrons. So the water here is going to absorb much of the radiation that's released from the nuclear reactor. And then that pressurized water goes and boils water, boils steam, and then turns a turbine. One of the problems that we have in the United States is that we usually use saturated steam for our turbines, to run our turbines. What we really should use is superheated steam. The saturated steam condenses on the turbines, which makes this turbine, it's less thermally efficient, and also you have to replace the turbines more frequently. So I forget how many reactors. I think we have 104 in the United States. That's on a future slide. We have 104 nuclear reactors, and we have 104 different nuclear reactor designs. We don't have a set design. That's one of the problems with nuclear power in the United States. We also have other types. We have a boiling water reactor where the water boils right in the nuclear core, and then it turns turbines. So there's different types. Okay, so how many plants do we have? Okay, United States. Yeah, we have 104. Okay. I was right. We're building more. Of course, they're all different designs. That's just the way we do it here in the United States, I suppose. And you can see France relies very heavily on their nuclear power. Japan used to, but after the Fukushima event, they decided not to dismantle their nuclear power facilities. Uh, they've turned away from it. Ukraine uses quite a bit. They have Lithuania on here. Lithuania is another country that uses quite a bit, not listed here. Okay. And nuclear power produces basically very little air pollution. So, of all of them, even like wind energy produces lower than that. Why do you need it? Well, because you still have to like ship things there. You have to truck the fuel around places. Same thing with wind turbines. You have to truck them there. You have to go and you have to fix them. These types of things. But at the same time, we have very expensive safety precautions, and then we've got some really gnarly nuclear waste that we have to deal with. So there are some bad things about nuclear energy. Although for carbon cycle, this is by far the best. And then what would be wonderful is if we can get nuclear fusion. So we are trying to do this nuclear fusion. This is how the sun gets its energy. And there's two types of fusion reactors. We have a tokamak. This is a Russian design where it uses high temperature to make a plasma to try and do nuclear. It does nuclear fusion. But the problem with the tokamak, we haven't quite figured out how to make it energy positive. So we can get nuclear fusion, we just can't get it to be net energy positive. There's another type of nuclear fusion. It's the Nuclear Ignition Facility in Lawrence Livermore National Lab. But that's more like they're more doing nuclear weapons research, but hopefully maybe one day it could be used for civilian use. But the idea there, they have a bunch of lasers they shine down onto a pellet, and then that has a nuclear fusion reaction that happens inside of there. But you can look online if you want to learn more about that. Okay, and solar energy. Solar energy is a very convenient one, and it is very diffuse, though. It has to be concentrated to be useful. And this is how I have my home has a solar water heater. I don't even turn on I have a hot water heater that's also electrical, but I don't even turn it on. I keep it off. I just use the active solar heater to heat my water, and it's great. I got all the hot water that I could ever want. But the idea, though, is that it has a pump that pumps water up and is heated by the sun. Photovoltaic cells, this is how you can get electricity from sunlight. They work pretty well. We're getting better, and we've gotten much better with using photovoltaics. Where they really work great is in space. I mean, using the PVs in space for satellites and space stations, those run very, very well. On Earth, there's a couple problems. Of course, they only work when the sun is shining. Of course, if we had an international worldwide grid of power, that probably wouldn't be as much of a problem. But we still have some issues with solar power. But solar power is great. And biomass, we can burn biomass. We don't do this as much in the United States, but especially not for electricity, I should say. Other nations do it, of course. But we could use it as a small source. And it's just not very usable. Biomass is just not very usable. You take it and you have to pelletize it, and you have to dehydrate it, and then you can use it in our as a boiler. And honestly, the older boilers work better for this. So on Maui, for instance, we have a pretty old boiler, I guess, and we did burn some farm waste. We burned some of the sugarcane. Of course, we don't use sugarcane anymore, but the older technology works better. It's less. It doesn't have as many controls, so it's a little bit more fail-proof, and you don't have to have as consistent products going in. Hydrogen. So this would be a great fuel to use. It's very cleanly burned, so this may be a fuel of the future, but it has its problems. It's as explosive as can be, and also you can't see the flame because it doesn't have any soot to it, so a hydrogen flame is invisible. and at least to visible light. Of course, it would be visible to infrared and whatnot, but it's hard to see, and it's also explosive. So one thing about having a hydrogen fuel tank, it would be very explosive. You have to electrically ground it to make sure it doesn't cause embrittlement. Okay, and fuel cells. Well, the NASA uses fuel cells for the they not anymore. We don't have our space flight uh, project anymore, but hopefully it starts up again soon. But we used fuel cells in the Apollo space program and in the uh, in the space shuttle program. It would be nice if you can use fuel cells for conventional fuels like gasoline, because these would then would increase the efficiency by a huge amount, from at least 3 times the efficiency. But we'll see. We're still working on it. Wind and water. Wind is it's hard to use wind. Wind is not very consistent, and it tends to send spikes of energy in. We're getting better at using it though. Water is very useful. Water is amazingly useful and really, really small, but we're using these more and more. Hydroelectric has been used for a long time. It's a very good sort of electricity. Wind, though, we're working on it, like I said, but it's not as effective as other things. Geothermal, depending on where you live, it can be also not even for heating, can also be used for cooling. Like instead of using air conditioning, you can use geothermal to like the earth to cool, to lower your electricity bill that way. But in areas you can use the heat from the earth to generate steam. And some of the places they use this, like in Iceland, they do this quite a bit. Use a lot of geothermal energy in Iceland. And ocean thermal energy, we've seen that we could use this in a while. Also tides. So the thing with tidal energy, it wouldn't be a very good use in Hawaii. It'd be better used. It's better used in nearer the poles. So Alaska and New Zealand would be a great place for tidal energy, because the tides are much greater at the poles, not so much in the tropics. So better source there. Geothermal would be great in Hawaii, of course. So how much is too much? So our demand for energy is increasing. So what's going to happen for the future? And you can see here, U.S. and China, we're using quite a bit. So we're using quite a bit of energy. And energy needs are increasing. Also, economies are emerging. India has already surpassed China in its population. And it's going to start, it's going to be up there soon. So what are we going to do with the emerging economies? And our own economy is still growing. And by far the most useful is electricity. And you can see here it has changed. We had a previous slide and see it's changed. So less coal is being used, and we're using more natural gas. So we will see. We will see what happens in the future. So, and that is the end of this slide. Then the talk. I will see you for the next one.